For this section, it starts with the generality of relative validity. It does appear that some laws of conditioning can sometimes show generality. For example, relative validity effects which illustrates the point that conditioning occurs to the extent that the CS provides information about the US. Wagner reported that the relative validity effect is in various experiments, such as fear conditioning in rats, operant learning in rats, and eye blink conditioning in rabbits. It appears in even wider range of species using a variety of conditioning preparations, such as human participants. Bitterman, Kluvillen, and associates at the University of Hawaii did experiments with honeybees that showed, despite such different brains, the behavioral principles of learning seem similar. Again, the generality to relative validity effects was shown. Associative learning in honeybees and humans was the next section. It begins with conditioning in bees. There was a focus on foraging honeybees with an approach that emphasizes the fact that learning fine-tunes an animal's natural behavior and built-in predictions. The fact is, learning may allow bees to know which colors and which odors are relevant in their search for food. Honeybees clearly do learn about flowers with parallels to principles previously discussed, such as summation, overshadowing, sensory preconditioning, compound potentiation, and relative validity. Animals become frustrated when a reward is smaller than expected, a concept observed in honeybees as well. This concept is known as successive negative contrast effect. Although honeybees make for good animal subjects to generalize, not everything works in bees the way one may expect. For example, conditioned inhibition produced in classical conditioned inhibition or feature negative procedure has been difficult to show in honeybees. However, they may still be able to find it in the right experiment later on. Blocking was originally unable to be found in honeybees when it involved color and odor, as it was in vertebrates. However, it occurs when the compound was made up of two CSs from the same modality, for example, odor and odor, or color and color. Still, many unknown similarities and differences between human and non-human learning, however, there are still differences. There is an impressive generality to known conditioning principles. Category and causal learning in humans was discussed next. Conditioning principles have also been important in recent works with associative learning in humans, two situations in particular. First is category learning, which is when humans learn to classify items as belonging to one category or another. For example, it is what is in front of me, a cat, a dog, or a bagel. This shows how we tend to think that all items are made up of many features, and that categorization depends on learning to associate the right feature with the right category. The second is causal learning, in which people learn about the cause of a certain effect. The idea that certain cues or causes become associated with certain outcomes or effects. Humans show blocking effect and condition inhibition. The research used to explain this generated considerable interest in whether models of conditioning, especially Rescorla-Wagner, can handle categorization and causal learning problems. Rescorla-Wagner have their equation, which is similar to that cognitive philosophy uses to change the strength of the connections between units in connectionist networks. Connectionist models can describe categorization. This shows that although the Rescorla-Wagner model is thorough in explaining, other models of classical conditioning may also do the same. Shanks and his proposal of relative validity results in the symptom-disease situation. He proposed the simple connectionist network model. Nodes or units on the left side of the model correspond to features, such as symptoms, while the nodes or units on the right side of the model correspond with categories, such as diseases or conditions. All the network does is learn to associate the feature with the categories, following the Rescorla-Wagner rule, and therefore this is essentially a new presentation of the model predicting the same things the Rescorla-Wagner model predicts. Two features will compete with one another to gain connection with the category. The network will produce blocking effects, over expectation, overshadowing, inhibition, etc. That was all for this section.